Hello my dear students, welcome back to our channel. In the last video we have discussed event, types of events and algebra of events like A or B, A intersection B, etc. And today we can discuss mutually exclusive events and exhaustive events. If you are watching this channel for the first time, please subscribe to our channel. And if you find this video useful, please like, share and comment. Okay, we can go to the video. Mutually exclusive events. Two events are said to be mutually exclusive if they cannot occur simultaneously. That is, if one event occurred, then the other one cannot occur. That is, their intersection will be empty. If A and B are two events, then A intersection B is equal to empty, disjoint in case of mutually exclusive events. For example, we can say in tossing a coin, if head occur, then tail cannot occur. Like that in tossing a die, we can say if number 1 occur, then number 2 cannot occur same time. Or other example, we can say consider the experiment of rolling a die. Then S is equal to set 1, 2, 3, 4, 5, 6. Then A be the event of odd numbers and B be the event of even number occur. Then what is A? A equal to set 1, 3, 5 and B equal to set 2, 4, 6. Here A intersection B is equal to empty. We have already told that in tossing a coin, event of occurring a head and event of occurring a tail are disjoint events. Like that in throwing a die, each simple events, that is set 1, set 2, getting a 3, etc. are mutually exclusive events, or we can say all simple events of a sample space are always mutually exclusive. Or if we take any simple events, they will be mutually exclusive. So we can say the definition of mutually exclusive events as two events A and B are said to be mutually exclusive if the occurrence of any one of them excludes the occurrence of the event. That is, if A occur, then B cannot occur. Example for not mutually exclusive events, we can say consider the experiment of rolling a die and let A be the event of getting an odd number and B be the event of getting a number strictly less than 4. Then B is equal to set 1, 2, 3. Here A intersection B is equal to 1, 3. So A and B are not mutually exclusive. Next, we have exhaustive events. Some events are said to be exhaustive if their union is equal to the sample space itself. Or we can say if even E2, etc. En are n events of a sample space F, and if even union E2 union etc. union En is equal to S, then even E2 etc. En are called exhaustive events. That is, even E2 etc. En are called exhaustive events if their union I from 1 to n is equal to sample space itself, or even union E2 union etc. union En is equal to sample space, then it is called exhaustive events. For example, we can say in tossing a coin, let E be the event of occurring a head and F be the event of occurring a tail, then E union F is equal to HT, that is S. Then it is an exhaustive event. Like that in throwing a die also, if we take all simple events, S is equal to 1, 2, 3, etc. 6. If we take all the simple events, that is getting E1 is equal to getting 1, E2 is equal to getting 2, etc. E6 is equal to getting 6, then their union is equal to sample space. Then these are called exhaustive events. Another example we can say, consider the experiment of throwing a die. Then sample space is equal to 1, 2, etc. 6. Let A be the event of getting a number less than 4 and B be the event of getting a number greater than 2 but less than 5. That is 2 less than x less than 5. And C be the event of number greater than 4 appear. Then what is A, B, C here? A is equal to less than 4, that is 1, 2, 3. And B is equal to greater than 2, less than 5, that is 3 and 4. 3, 4. C is equal to greater than 4, that is 5, 6. What is A union B union C here? A union B union C is equal to set 1, 2, 3, 4, 5, 6. So here A, B and C are exhaustive events. Here see, the intersection is not empty. A intersection B is 3 here. So intersection need not be empty in case of exhaustive events. Or in other words, we can say E1, E2, etc. En are called exhaustive events if at least one of them necessarily occur whenever the experiment is performed. One more definition: mutually exclusive and exhaustive events. As the name suggests, it is mutually exclusive and exhaustive. That is, if we have E1, E2, etc. n events, then if each events are pairwise disjoint, that is EI intersection EJ is equal to empty for I not equal to J. That is, E1 intersection E2 is equal to empty, E1 intersection E3 is equal to empty, E2 intersection E3 is equal to empty. Like that, all pairs are empty, mutually exclusive, and their union is equal to the sample space itself. Then E1, E2, etc. En are called mutually exclusive and exhaustive events. The best example we can say in an experiment, all the simple events. For example, in tossing a coin, let E be the event of getting head and F be the event of getting tail. Then they are disjoint and union is S. Or in throwing a die, all simple events, that is set 1, set 2, that is E1, E2, etc. E6. They are pairwise disjoint and union is S itself. So if we take all the simple events of an experiment, then they are mutually exclusive and exhaustive. We can see more examples. Example: two dice are thrown and the sum of the numbers which come upon the dice is noted. Consider the following events associated with the experiment. A. The sum is even. B. The sum is a multiple of 3. C. The sum is strictly less than 4. D. Sum is greater than 11. Which pair of these events are mutually exclusive? Here two dice are thrown. We know the sample space S is equal to, there are 36 elements. Event A equal to, the sum is even. In the first row with the first die showing 1, we know 1 1 is even, 1 plus 1, sum is even. Like that, all odd pairs 1 3, 1 5 are even. And in the case of second row, first die showing 2, we know 2 2 is even. Like that, all even pairs 2 4 is even, 2 6 is even. Like that, 3 1 is even, 3 3, 3 5, etc. We know 6 2, 6 4 and 6 6. Write all the elements, don't write like etc. Okay. Next, B be the event, sum is a multiple of 3. Sum is multiple of 3, that is multiple of 3 we know 3 6 9 12. So sum is 3. First one 1 2 is 3 and 1 5 is 6. In the first row, sum is a multiple of 3 over. In the second row, 2 1 is 3 and 2 4 is 6 over. 2 6 is 8, not 9. Next, in third row, 3 3 is 6 and 3 6 is 9. Third row over. Next, in the fourth row, 4 2 is 6 and 4 5 is 9 over. In the next row, 5, 1 is 6 and 5, 4 is 9. In the sixth row, 6, 3 is 9 and 6, 6 is 12. Multiple of 3. C is the even, sum is strictly less than 4. So in the first row, 1, 1, 1, 2. Next is 1, 3, that is 4. So it will not include. Like that in the second row, 2, 1, 2, 2 not included, 2, 2 is 4. Over. In the next row, see 3, 1, 3, 1 is 4. All others are greater than 4. So this is C. And D is sum is greater than 11. That is sum is 12. Only one element, 6, 6. To see which pair are mutually exclusive, we have to see A intersection B, A intersection C, A intersection D, B intersection C, B intersection D. Okay, we can check. Here A is sum is even, B is sum is a multiple of 3, C is sum is strictly less than 4, D is sum is greater than 11. See here what is A intersection B? A is sum is even and B is multiple of 3. What is the even numbers that is multiple of 3? That is 6 and 12. 3 and 9 are odd numbers. So sum is 6 and 12. Here then what are the elements? 1, 5, 6 and 2, 4, 6, 3, 3, 6, 4, 2, 6, 5, 1, 6 and 6, 6 is 12. So this is A intersection B. This is not equal to empty. So A and B are not mutually exclusive. Like that you can see all. Okay, next A intersection C. A intersection C is equal to A is sum is even and C is sum is less than 4. What are the even numbers less than 4? 2. So we can say sum is 2. 1, 1. This is a singleton set but not equal to 5. So this is not mutually exclusive. Next we can see A intersection D. A intersection D is A is even, D is greater than 11, that is 12. One element 6, 6. 12 is both even and greater than 11. So this is also not equal to empty, so not mutually exclusive. Like that you find every pair. Next we can see B intersection C. B intersection C is B is sum is a multiple of 3 and C is sum is strictly less than 4. That is sum is 3. That is 1, 2 sum is 3 and 2, 1 sum is 3. This is also not equal to 5. So this is also not mutually exclusive. Next we can find B intersection D. B intersection D is B is sum is a multiple of 3 and D is sum is greater than 11. That is 12. Set 6, 6. Also not equal to 5, not mutually exclusive. Last pair C intersection D. C is strictly less than for sum. D is strictly greater than 11. They are disjoint. So this is empty and so this is mutually exclusive. So we can say C and D are mutually exclusive. All others are not mutually exclusive. Next example, a coin is tossed 3 times. Consider the following events. A. No head appears. B. Exactly 1 head appear. And C. At least 2 head appears. Do they form a set of mutually exclusive and exhaustive events? So mutually exclusive means disjoint. Exhaustive means union is S itself. So we can see whether they are pairwise mutually exclusive and exhaustive. Okay, here S is equal to a coin tossed 3 times. So S is H, 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 T, H, T, H, H, T, T. Next case of T, T, H, H, T, H, T, 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 H, T, T, T. 8 elements. Next A. A is no head appears. That is T, T, T. And B is exactly 1 head appear. That is HTT, THT, TTH. HTT, THT, TTH. That is only one head. And C is at least two head appears. That is the case of two heads and three heads. Three heads, HHT, HTH. Here only one head. Here two head, over. So HHH, HHT, HTH, and THH. Now we can see whether they are pairwise disjoint. So A intersection B. A intersection B is empty. That is intersection of no head and exactly one head. Of course empty. Next A intersection C. A intersection C is A is no header and C is at least two header. So it's also empty. And B intersection C. B intersection C is B is exactly one header. C is at least two header. That is greater than or equal to 2. Here 1, here greater than or equal to 2. So this is also empty. So they are pairwise disjoint. Now see A union B union C. A union B union C is write all the elements. Here TT, TT covered. Then HTT, THT, TTH. HTT, THT, TTH. And HHH, HHT, HTH, THH. So all the elements covered, which is equal to S itself. So they are pairwise disjoint and their union is S, exhaustive also. So we can say they are mutually exclusive and exhaustive. So this is all about mutually exclusive events and exhaustive events and the case of both. So the terms related to probability is over. Next video we can see the axiomatic approach of probability. If you find this video useful, please like, share and comment. Thank you for watching. Thank you.